it is a frequent occasion that one has to solve the following equation. Where this is some field phi, scalar field phi, and y of x is some source. We encounter this in our GR lectures, but this is much more simpler settings in some sense. So where this guy box is D'Alembert operator, so it's d mu, which is the same as dt squared minus Laplacian, which is the same as dt squared minus dx squared minus dy squared minus dz squared. So how does one solve this equation? If one knows the solution of this equation, where D'Alembert operator acts on x, only on x, and y acts as a parameter, then the solution of this equation can be found. Well, before saying that, let me show what happens here. This equation is invariant under the shift of x. If I simultaneously shift x and y, this equation doesn't change. Then it means that g is necessarily function of difference, x minus y. So if we know this function, then the solution of this equation, phi of x, is easy to find. It's just integral over d for y, gx minus y, times g of y. Indeed, why do we know it? Because if we act by D'Alembertian on both sides of this guy, then D'Alembertian on the right-hand side acts only on this guy. So then it means box of phi of x is nothing but d for y, box acting on x, x minus y, g of y. But this guy is nothing but the delta function. So continue this equality. We have d for y, delta for x minus y times yacht of y. But here we have 4 integrations and 4 delta functions. Delta 4 of x minus y is just delta x0 minus y0, x1 minus y1, and so forth up to 3. So we have product of 4 delta functions and 4 integrals, integral of y0, y1, y2, etc. So taking all these 4 integrals with 4 delta functions, we obtain yacht of x. So we obtain this equation. So indeed, this phi of x solves this equation. Now we want to find the solution of this equation. This is so-called green function for the D'Alembert operator. How do we do that? Well, we do Fourier transform of both sides. First, Fourier transform of the delta function, x minus y, is just d for p over 2 pi to the 4th, exponent of a k mu x minus y mu without any division. So this is the Fourier transform of the delta function, which is according to the rule that delta of x is just dk d pi over 2 pi. Sorry, here is p mu dp I pi x. So product of 4 delta functions is product of 4 integrals, and the product of 4 exponents is just this guy. So this is trivial. This is a Fourier transform. Now we want to consider Fourier transform of x minus y. We define it as d for p over 2 pi to the 4th, some g twiddle of p, exponent of e, p mu, x minus y mu. Okay. Now, this is just by definition, so we take Fourier transform. Now, plugging this here, this here, and this here, we obtain the following situation, that the Lambertian acting on integral over d4 pi over 2 pi to the fourth g twiddle of pi a p mu x minus y mu equal to the integral over d4 pi over 2 pi to the fourth exponent of ep mu x minus y mu. The Lambertian acts only on this guy because this is the only guy who depends on x. But it's not hard to check that d mu, which is the Lambertian, acting on exponent of ep nu x minus y nu is nothing but minus p mu I p nu x minus y nu. This is a trivial exercise. If you know tensors, you can do it straightforwardly. Then, from here, what do we obtain? We obtain that combining everything on one side, we obtain the following situation: d4 pi over 2 pi to the fourth exponent of ep mu x minus y mu acting on p squared. P squared is just this guy. P squared g twiddle of p plus 1, and this is all equal to 0. Because this is the expansion of the complete basis of functions, this equals to 0 only if this equals to 0. As a result, we obtain that g twiddle of p is equal to minus 1 over p squared. P squared is p mu times p mu. So that was actually the reason to perform Fourier transform, because Fourier transform allowed us to convert differential equation into algebraic equation, and the solution of algebraic equation is very easy to find. What remains to be done is to calculate this integral with the substitution there of 1 over p squared. If we do that, we are done. We obtain actually there is one simple command. This is a solution of this up to the addition of some function cp, which when multiplied to cp times delta p squared for any smooth function of p, because you see delta p of p squared multiplied by p squared is just 0. But addition of this guy into here gives us something which is specified. Well, you see, the solution of this guy is always specified up to addition of the solution of homogeneous equation with the right-hand side equal to 0. And this term is important in this discussion. We will clarify this in a moment. Okay, so we are looking for the solution of this equation. And already have found that the solution of this equation can be represented as d4k over 2 pi to the fourth g twiddle k I k mu x minus y mu. And we found that g twiddle k is just 1 minus 1 over k squared, where k squared is k mu times k mu. It's a 4-vector, k mu, plus some smooth function of k times delta k squared. And if we plug this here, we obtain that gx minus y as integral over d4k over 2 pi to the fourth minus exponent k mu x minus y mu over k nu, which is k squared, plus g0 of x minus y. Okay, where G0 is the same quantity where this guy stands here. It is not hard to check, which is not a good exercise, that this G0 of x minus y solves homogeneous equation, exactly due to the presence of this quantity. And but the solution of this equation always is defined up to the addition of this thing. So in the following we'll drop it off, because we will always drop off this kind of terms, because again the solution of this equation is specified up to this thing. But let me stress one thing which appears here for this quantity. We drop this off for this quantity. This integral gx minus y integral over dk0 over 2 pi integral over d3k over 2 pi cubed I k0 x minus y 0 minus I k x minus y divided by k0 squared minus k vector squared. It is not hard to see that this integral from the mathematical point of view is not defined. In complex k0 plane, whether this is real part of k0, complex k0, imaginary part of k0, the contour of integration goes along the k0 axis, and it's stuck. There are two poles on this action. It says minus modulus of k, of this k, and plus modulus of k. So there is a problem. We cannot find this integral literally diverges. What should we do? Well, in this case, we have to use physical intuition and the fact that this solution of this equation is defined up to the addition of this. Well, what do we expect to get? What is the meaning of this quantity? What is the meaning of this? To understand the meaning of this quantity, let us for a second look at the following guy. X minus y. Who is this guy? The solution of this equation, phi x minus y, is proportional to x minus y modulus. And this guy is nothing but the Coulomb law in physical terms. And Coulomb law is the following thing, that we have a charge placed at the position y, and look for the field that it creates at the position x. So it's like two-point correlation function, so to say. We have a source at y, and we look at the correlation that it creates at the point x. So this guy is a generalization of this situation. So we have a source which is instantaneous in space and time. This is a source at position in space. This is a spatial problem. And here we have a space-time. So we have space-time. So this is x0, which is t, x1, x2. And we have a point y. And at this point, we have a source, instantaneous source. So delta function can be understood as if it is not 0 at one point y and 0 everywhere else. So this source creates something outside of this source. The right-hand side is 0. So the solution of this equation describes something which travels with the speed of light, because this is a wave equation describing waves traveling with the speed of light. So the solution of this equation should be not 0 on the light cone, which has apex at the point y. So it should be non-zero only on the light cone, because it describes some excitation which travels with the speed of light and passing through the point y. What do we expect? On physical grounds, we expect it to be non-zero only in the future light cone. So only for the x's which are sitting here, for the point x mu, which sits on the future light cone, it should be not 0. But it should be 0 here, because you see, the source created an excitation which travels with the speed of light in future, towards the future, but not towards the past. So we want to look for a solution of this equation, so-called retarded green function, which is not 0 on the future light cone from the point Y. So let me say that this statement specifies how we define the contour of integration. The contour of integration we define according to this rule. We will see now that if we go around these poles according to this rule, then this guy is 0. So if we define the contour here, the contour of integration over K0, like this, then we obtain the retarded green function, which obeys the following property, that it is 0 if x0 is before than y0. It is 0, but it is not 0 if x0 is after y0. We will see that the specification of the contour has to do with this property. And if we would choose a different contour, that would correspond to the solution of this equation, which is different from the one which we are considering by the addition of something like solution of homogeneous equation. So we have to calculate this integral gx minus y, which is minus dk0 over 2 pi, integral over d3k over 2 pi cube, exponent of ik0 x0 minus y0 minus ik vector x minus y divided by k0 squared minus k vector squared. And the contour of integration in the k0 plane, let me draw it. So we have k0 plane. The contour of integration in this plane goes along the real line, and it has poles here, minus k and k, where k is just modulus of this k. And I told you that we have to specify the contour like this, that it goes around the pole like this. So our contour is like this. Now, why is just because if the contour, let me call it C, goes like this guy obeys the property of the retarded green function, retarded. The reason for that is the following. Now, consider that the situation that x0 is before than y0, which means that this quantity is negative. If this quantity is negative, I can close the contour in the lower plane by infinite hemicircle, half circle, according to this rule. Why? Because on this circle, the integrand is always 0. Because when this negative, on this circle, the imaginary part of k0 is minus infinity. As a result, the exponent is 0. And I add nothing to this integral over this contour. I add nothing along this contour for this guy being negative. The integrand is 0. So, but this contour doesn't have inside any, for this contour, the integrand doesn't have inside any singularities. It is a holomorphic function of k0 inside this contour. So according to the Cauchy theorem, for this case, we obtain that gr x minus y is 0 if the contour is defined like this. Now, if x0 is greater than y0, this quantity is positive, and we have to close the contour in the upper plane. And as a result, for the same reason as we have to close. But in this case, our contour encircles some poles, and the integral should be taken, is not 0, and should be taken according to the Cauchy theorem. According to the Cauchy theorem, this guy, well, it's a home exercise along this contour, this guy is equal to, so I mean this integral. I'm not going to give too many details, this is a home exercise, to take this integral, it is equal to minus exponent a k, this k, x0 minus y0 minus exponent I divided by 2ik. And we should bear in mind that this is all true for the case when x0 is greater than y0. So, as a result, we have to take the following integral. gr x minus y is minus heaviside theta function of delta x0. Delta x0 is just x0 minus y0. So this function is 1 if x0 is greater than, and 0 if x0 is less than y0. Integral over d3k, so plugging this into here, what remains to be done is to take this integral minus k vector delta x vector. Delta x vector is just this. This is delta x vector multiplied by this I k x0 minus y0 minus I k x0 minus y0 divided by 2ik. So how do we take this integral? To take this integral, we do the following. We use, instead of k1, k2, k3, we do transformation to the polar, to the spherical coordinates in the k space, to k, modulus of k, theta, and phi, where the angles in the spherical coordinates. And direct delta x along the third direction, such that k times delta x is just modulus of k times delta x times cosine theta. So what do we obtain then? Then this integral, continuing it, let me continue it, this integral acquires the following form. So we have theta function of delta x 0, we have 2 pi cube here, integral from 0 to plus infinity dk times k squared, and we have integral over d phi. Nothing depends on the integral over the phi, so integral over d phi gives us 2 pi. What remains to be taken is the integral over d theta is, we have sine theta times d theta, so this is d cosine theta from minus 1 to 1. This is the integral over the d theta times the integrand. The integrand is just minus ak modulus of delta x times cosine theta times this exponent ak x0 minus y0 minus ak x0 minus y0 divided by 2ik. Well, taking the integral over the dk, over d theta, d cosine theta, with this, we obtain the following theta function of delta x0 divided by 2 pi squared. Here, actually, one of the k's cancels with k squared. What remains is the following integral over dk. dk times k divided by I minus ik delta x modulus, exponent of minus ik modulus of delta x minus ik modulus of delta x multiplied by the exponent, well, exponent of ik delta x 0 minus ik delta x 0 divided by 2i. So k cancels here. Delta x can be taken out. 2 together with I can be also taken out. So what remains is just the product of two brackets. If we expand the bracket, we obtain 4 terms. Product of this to this and this, and this to this and this. But then we can reshuffle these 2 terms, these 4 terms, such that we obtain the following expression. Delta x0 divided by 4 pi divided by modulus of delta x, and integral from minus infinity to plus infinity, dk. So reshuffling is the following. We combine 2 of the 4 terms into the integral from 0 infinity to plus infinity, and in the other integral we change k to minus k and convert it into the integral from minus infinity to 0 of the same expression. So we obtain that 4 terms are combined into 2 terms for the integral from minus infinity to plus infinity. I hope it's clear what I mean. So the result is the following situation. ak delta x0 plus modulus of delta x minus xi k delta x0 plus delta x modulus. Okay, but these integrals are very simple. They just lead to delta function. So what do we obtain? Theta of delta x0 divided by 4 pi modulus of delta x times the following delta functions. Delta, sorry, here is minus sign, and here is a plus sign. Delta x0 plus modulus of delta x minus delta function delta x0 minus delta x. Sorry, vice versa. Here is minus, and here is a plus sign. But the argument of delta function for delta x0 positive, the argument of the delta function is never 0. So this can be dropped off. And as a result, what remains is the green function, which we use in the calculations in our lectures. You see, it is not 0 exactly on the light cone when delta x0 is equal to the modulus of delta x, which is a light cone condition, and towards the future of light cone because of the presence of this delta function, and decays with the distance as the inverse modulus of the distance. So I hope it's useful for the lectures.